Hello, everyone. Today we're going to talk about clustering with igraph. So last week we talked about visualizations of our graphs in igraph, and today we're going to take it up a notch to take a look at how it can help us with detecting communities. So I will share my screen. Okay, so community detection and networks. We need to break that down just a little bit. So we're talking about community discovery. First of all, what is a community? Communities can also be called clusters. They could be called modules. This is simply a group of nodes with dense internal connections, but few connections to other members of another community. So what this looks like is on the right here, we have these two communities, one on the left and one on the right. We can see that they are densely connected to each other and they have few connections between them. So we would have a left community and a right community. We can also visualize this in an adjacency matrix form. So these two diagonals on the upper left and the bottom right, we have a lot of dense connections, and that is indicating the connection between two nodes. So, but just by looking at the adjacency matrix, we can probably see that we have two communities in our data. So community discovery is simply, given a graph, we want to divide it into good communities, and we'll talk about what that means coming up. There are a few resources that I'd like to point you to. First one is Newman and Girvin, 2002, Community Structure in Social and Biological Networks, as well as this lovely review by Fortunato, 2016 on arXiv. Okay, so for community detection, there are two main questions. Number one, how do we find good communities? And number two, what will these communities correspond to? Or how do we make any sort of biological interpretations about what the data is telling us? So step one, how do we find these good communities? So we, again, identify clusters of nodes that are more connected to each other than they are to things outside of their cluster. And what good means in this sense is we have high modularity. And to take a look at what modularity means, we're going to look at an example of unweighted edges in a network from freecodecamp.org. So on the right here, we have a very small network of different websites representing these different nodes here. We've got sizes that represent the connectivity, and the colors represent the community that they were defined to be into. So what we do is we look at our adjacency matrix, and we can pull out some stats just from this adjacency matrix. So each website, again, is the name of a row and a column. They have a 1 if they are connected by an edge at all. And the people that made this network, they assigned an edge if the Wikipedia page for each website mentioned the other website. So that's how they were able to decide if there was a 0 or a 1. So in order to identify the degree, which is denoted as K, we simply add up the contents of each row. And so that's what we have here for GitHub, has a degree of 2, Google has a degree of 7. We can take a look at our graph and see what that looks like. So Google, we can count, has 7 edges, while GitHub only has 2. From this, we can add up all of our degrees and divide by 2. This gives us 14, or L, the number of linkages or edges. And finally, just adding up the nodes, we have 8, and that is denoted as N. So getting back to modularity, we can use all of these parameters to get the modularity score. It looks kind of scary at first, but when you break it down, it's not too bad. And so here, this just means we're going to divide everything that follows by 2 times the number of linkages that we have. This here indicates the value in the adjacency matrix A at row I, column J. This whole thing just means the difference between the network's real structure and the expected structure of a random network. And then finally here, this is what's called the Kronecker delta function. Simply, it's just 1 if I and J are in the same cluster and 0 if they are not. So modularity is bounded between the values of 0 and 1, with higher values indicating higher modularity or a better job of identifying clusters. So here we have an example of high modularity network with red community and a yellow community. with lots of connections on the left and right and only one between them, whereas lower modularity, we have a mix of the two here. So modularity simply serves as a measure of the quality of the partition. igraph has many functions used for module detections that optimize this modularity score. The two that are in the R code that is on the repo now, we have cluster fast greedy and cluster Louvain. I'm not going to read all of these, but these are simply here for your reference. It calls out to the manual page for igraph that discusses what the detection algorithm is doing. And then if you are unfamiliar with some of the nomenclature that's used, this is a lovely link that will explain some of the words. In addition to those two, igraph also has random walks, label propagation, leading eigenvector, edge between us, and spin glass. The thing to note is that most of these algorithms only work on positive connections, which means in order to do modularity detection in your networks, you first have to take out all of your negative connections in order to go forward. The only exception to this might be spin glass, but I have never used spin glass, so that should be interesting. So back to our main questions, we identified how do we find good communities, but the next thing, bringing it back to the science, is what are these communities corresponding to? So going to our very small network here, the modularity analysis identified 3 different communities, and they are colored here. So just taking a look at what is in the yellow community, we have Google, Quora, and Wikipedia. And just knowing what we know about these websites, these are information and reference websites, so that's pretty easy to assign what that means, what that community grouping means. Very similar in the case of the blue community here, we have GitHub, Twitter, and Medium. Those are all online publishing websites. Something that's probably not too intuitive is YouTube and PayPal. YouTube, I didn't know this, was founded by former PayPal employees. So that might be the reasoning behind the community detection of these two being in one community. But without like prior knowledge or insider knowledge, it would be really hard to understand why those two were linked together or in the same community. So bringing this to a biological example, this is a paper called A Global Atlas of the Dominant Bacteria Found in Soil. And what they did is Spearman correlation analysis of different phylotypes of bacteria that are inhabiting different types of environments. Along with the microbiological information, they also had information about aridity and temperature. And so they use cluster analysis to guide correlation between different phylotypes of their bacteria and environmental parameters. So here in figure B, this is the results of their Spearman network. They performed modularity analysis and detected different communities. Once they had these different communities assigned, they went back to their data and mapped out the abundance, normalized as z-score, to different environmental parameters. And these are the things that popped up as significant. So for example, this blue community here, when they plotted it against pH, they saw that this could be called their high pH community, composed of 108 different phylotypes. And so they just did this iteratively with all of their clusters and all of their environmental parameters to understand how they could label or make sense in a biological way of all of their data. So with that, I will call your attention to our R code that has been put on the repo. This just walks you through taking our network from last time and performing cluster analysis on it using those two algorithms. Before the cluster analysis, we also have some different network statistics like betweenness and I think connectivity and assortivity. You can read about those, and we'll probably get into those in a little bit more detail in future lessons. But this is just a quick and dirty guide to how to set up the syntax for modularity analysis in igraph, and I hope you have fun playing around, especially if we're interested in taking a look at connecting our communities as defined in the network back to more biological information and being able to make biological inferences about our networks. Okay, thank you.